Hello, everyone. This is Jason Montgomery with EE Tech and All About Circuits. I want to thank all of you for joining us for what I think is going to be another outstanding live webinar session. Today, we're working with Murata, and the title of today's webinar is Design Requirements for Parallel Load Sharing. Let me tell you a little bit about our presenter and a couple of other small logistical items, and then I'll get out of the way and let Bill do his thing. So our speaker today is Bill Smith. He's the Director of Product Marketing Board Mount Power at Murata Power Solutions. And with more than 20 years of power industry experience, he has extensive knowledge in a broad range of disciplines. That's including process engineering, project management, test and qualification, field applications engineer, and much more. He got his BSET in 1991 from Roger Williams University, and we're really excited to have him here with us today to go through this session. So before I hand it off to Bill, just a couple of more things to keep in mind. Everyone, again, this is a live webinar session that we're up to here today. So if you've got questions for Bill that you would like to have answered, make sure to go to that Q&A box, the Q&A widget down on your screen, which will let you submit questions directly to Bill that we'll cover in a live Q&A session afterwards. This will be available on demand also afterwards if you want to catch another part of this again and make sure to get what's going on here. So with that, I'll step out of the way here, and Bill, thank you so much for joining us.
Thank you, Jason. So today we're going to talk about some of the basic design considerations for an N+1 parallel power supply. We're going to focus on a couple of modules, newly released modules from Murata, the DSQ and the DSE series modules. So the agenda topics for today. We'll talk about applications for N+1, fault tolerance. We'll talk about what considerations you need to make when selecting a power converter for an N+1 application, PCB layout essentials, thermal considerations, startup considerations, and how we're going to review your design for load share accuracy and thermal requirements. And then we'll have a quick follow-up with a couple of recommendations for N+1 power modules in a 600-watt quarter brick and a 400-watt eighth brick. So here is a simple diagram of a system that has an N+1 source. So most networking and telecom sources are N+1 because if the main system fails, whether it be an AC supply or in this application of a remote radio head, a diesel or a solar generator is generating the power for this system. So the front end of this system is N+1 reliable. In this particular diagram, we have two modules running in parallel. Each one of these modules is delivering 50% of the power to the electronic system. And this is a high reliability system. So in the event of a system failure, in other words, the two intermediate bus power supplies, if one of these converters fails short, the other converter will pump all of its current into that module and the system will fail. So this is not an N+1 redundant system right here. For an N+1 system, you need to have protection in case of one of these modules failing short in the O-ring diodes shown in this circuit. So if one converter fails, the O-ring diode blocks the current to that converter, and one converter can supply the complete load to the system. So that brings up a question. So each one of these converters running at 50% load is no problem. you need to rate each one of these converters to be able to supply the entire load. So here's a simplified schematic for discussion purposes. So going forward, we're going to be talking about an example here where we need a 12-volt intermediate bus rated at 600 watts at 55 degrees C with 200 linear feet per minute airflow. The input range is 36 to 60 volts, and we need an N+1 reliable system. First thing we want to talk about is what is an intermediate bus converter? Well, you have the main input power source, which we discussed before, coming from a diesel generator and a battery backup system. The intermediate bus is all of this circuitry, with the heart of the system being the board mount power supplies. We'll talk about typical input filter requirements for a network telecom application. The possibility of using a hot swap controller. Again, the networking and telecom system voltage never goes down. So when you're connecting your system to that power system that never goes down, you're going to be hot plugging it. So there may be some requirements in your system for a hot swap controller. Need to consider the input capacitors. Best thing to do is look at data sheets for that, but those also come into play with the input filter design. Need to consider the on-off control circuitry. So bringing up the power supply, you want to synchronize the on-off control for the intermediate bus converters. You want to consider the output capacitance. Many converters will require a certain amount of output capacitance for stability. Need to consider the O-ring circuit that's going to be used. And you need to consider the synchronization of your, in this case, multiple point of load converters. Quick discussion about point of load converters. Now the load may be a computing system or it may be a radio head, but within these systems is usually a microprocessor that has a core voltage and has I/O, and you may have analog voltages. You could see, 8, 10, 12 different voltages required in one of these loads. So you need to pay careful attention on how you synchronize and start up all of those point of load converters. So selecting a power module for a load sharing application. You need to definitely choose a module that is designed for use in an N+1 parallel configuration. One option is group mode current sharing, which the Murata power supplies will provide. In a group load current sharing, a little discussion about group mode current sharing. So the output of the module will actually look like an impedance of about 7 milliohms. So at no load, the output voltage will be 12 volts. At approximately 50% load, the output voltage will be 11.6 volts. And at full load, the output voltage will be 11.3 volts. Now this is intentional because of the output impedance to improve the current sharing accuracy of the modules. Now to get ideal current sharing, the output voltages of each model have to be exact. So to improve the current sharing, we trim the output voltage at 50% load during production to within plus or minus 1%, in this case of 11.6 volts. This will produce the best current sharing for a group load module. So if you go through all the calculations with a 0.7 milliohm output impedance and the trim accuracy, you come out with approximately 7%, plus or minus 7% accuracy for load sharing. We specify it at plus or minus 10% for margin and safety. So what are the advantages and disadvantages of group load sharing? One of the advantages is it's very simple to interconnect these modules. You connect the input and the output, and basically they will load share. There's no master-slave operations. Other suppliers may offer modules that are designed for current sharing, and that will require an interconnection between the two modules, either analog or digital, and that will require setting one of the modules up as a master and the others as slaves. This can be very difficult in a N+1 application, where if one module fails, the others have to take over. So a lot of external circuitry will be required with a master-slave configuration. And the group mode load sharing will be the lowest cost N+1 solution for an intermediate bus. So what are some of the limitations? We talked about the voltage regulation being approximately 5%, plus or minus 5% of the output voltage, nominal. In an intermediate bus application where your load is point-of-load converters, those point-of-load converters have an input voltage range normally of 7 volts to 14 volts. So the slight droop in the output of these modules has no effect on those converters. In the load share accuracy, specified at plus or minus 10% between modules, you may have an application where you need very high, a very tight regulation of the output. This may not be a solution for that particular application. But for an intermediate bus converter driving point-of-loads, this is the lowest cost solution available. So you need to consider the required power and operating temperature range for the modules. As we discussed earlier, two modules sharing a 600-watt load, you'd think that you only need 300-watt capability from each module. Well, that's not true in an N+1 situation, because if one module fails, the other module has to keep the system up and running. So you need a 600-watt power module. Temperature is an important factor. As you can see here, the brown line, and this is at 55 degrees C. You follow the 55-degree line up to where it crosses, and you can see that the module is capable of 450 watts with 100 linear feet per minute airflow. Increase that airflow to 200 linear feet per minute, and the module is capable of 500 watts. Again, increase the airflow to, let's see, it's 600 linear feet, and now the module is capable of 540 watts at 55 degrees C with 400 linear feet per minute. Of note here should be that these tests in many of the data sheets, competitor data sheets, are the same. These are tested with only the base plate. Okay? When you add an additional heat sink to the module, this further improves the thermal derating, and we'll get into that a little later. So N+1 circuit options. You could go with a standard O-ring diode at the output. It works. But if you take a look at the chart in the right-hand side of the slide, at 10 amps through a typical O-ring diode, and this happens to be a Schottky diode, you can expect about 6 watts of power dissipation on that diode. Now we're talking about 25 amps in normal application for each one of these intermediate bus modules. So that's going to transfer into 15 watts of power that you have to manage. That's a lot of power you have to manage. That's going to raise the temperature of your system. It can cause you some long-term reliability problems. So the best solution is to use an ideal diode, which consists of a FET and a controller for that FET. And if you look here at the right-hand side of the slide, with the FET and the proper, with the O-ring controller and the proper FET, at 10 amps, we have less than 1 watt of power dissipation on that FET. Extrapolate that out to 25 amps, and we're talking about 2 watts of power versus 15 watts of power. I don't think I need to explain much more than that, but it's much easier to manage that power dissipation. It's going to produce a much lower temperature application and higher reliability. So Murata has used the LTC 4357. Now, that's a Linear Tech part, which is now Analog Devices. It's a very good product we've used on several of our products here at Murata, so that's a highly recommended part. Texas Instruments also has controllers, and Analog Devices has controllers on different part numbers that were designed before the acquisition of Linear Tech. All good sources for these types of controllers. So what do you need to consider on these controllers? A couple of bullets here. You need to use an N-channel FET that has the right rating for drain to source breakdown, and that's greater than the bus voltage you want to create. You want to pick a FET with the current rating. Now that's a good bullet. Again, we go back to the intermediate bus. Under normal conditions, each one of these FETs would be carrying 25 amps. In the event of a failure of one of those power supplies, all of a sudden one of these FETs would be carrying 50 amps. So you need to consider that failure mode when you're rating the FET. So pick a FET with the appropriate ratings and always refer to the manufacturer's data sheet. Component placement. The layout of your system is critical to the performance. Again, we talked about the EMI filter, and we'll talk about it a little bit more in the next couple of slides. But you want to design the EMI filter, and you want to replicate that filter in front of each one of the modules. So you want the filter to be exactly the same for each one of the modules. You want to mount that filter as close as you can to the source, so where the power comes into your application or your board, mount that as close as you can to that source. You want to use heavy conductors that can carry the current. On the input side, the current is a lot lower because you have a 48-volt input, but on the output side, currents can come up very high very quickly. Again, under normal conditions, two modules each would be producing 25 amps, but in a failure condition, you're going to be producing 50 amps. You need to rate the copper that's carrying that current at 50 amps. Down below here, you can see a cross-section of a board where they're using heavy copper, interconnected copper layers, to carry that current. Keep the external input-output capacitors as close as you can to the module, particularly on the output of the module where the output capacitors can actually help stabilize the circuit. And the input capacitors also cancel out any effects of the inductive nature of the input filter. So a stable system requires good input-output capacitor and layout techniques. Many times the input-output capacitors can be mounted on the opposite side of the board and get them very close to the input-output pins. Run traces for the control circuitry, in this case the on-off control circuitry. You don't want to run those on-off control pins underneath the unit where they might pick up. You want to bring those control pins outside of the unit, connect them all together, and get them outside of the potentially noisy environment of the switching DC-DC converter. Here's an example of a input filter. Most of our data sheets for our modules have a schematic of an input filter that's been tested to a CISPAR Class B specification. And we provide the schematic and we provide a list of components, recommended components to design that circuit. And I'm not the expert on EMI filter design, but we have experts available. And if you're considering this type of an application, we can certainly put you in contact with the right engineer to help you through these designs. But generally, you want good layout techniques. You want to run the ground planes underneath the modules to help protect against radiated and conducted emissions. Make the EMI conductors large enough so they don't turn into antennas and radiate the noise out of the system. Some more layout techniques and guidelines. Throughout the input power systems with wide copper planes rated to carry the current, and in an application like we're discussing today at 600 watts, you're most likely going to need multiple layers to carry that copper, that current. Keep the power traces as short as possible, reduce any radiated EMI. Interconnect the power planes using vias to keep the impedance low. And we use vias to conduct the heat out of the module. We call these thermal vias. As you can see in this lower picture here, this is actually the pad for a pin on one of the modules. The input and output pins are larger than any of the signal pins, and they can carry a lot of heat out of the module, as the power dissipating devices on the module are located close to the input and output pins. So this can conduct the heat out of the module down into the board where it can be spread out and dissipated. There's a couple of pictures here that show a typical application for a thermal via. This is not a power module here, but it's a good example of the heat source. And now these vias connected to the heat source are conducting that heat down into the board on multiple layers. The bottom picture is particularly interesting because it shows the dielectric of the power of the PC board on the top layer. Now the dielectric isn't a great conductor of heat, so it's imperative that you pull the heat out of the module using vias down into the board, layers of copper. Copper is a great conductor of the heat. Okay, here's some more examples of using large copper planes. They're great for conducting the heat. They're also great for shielding any of the noise generated by the system. And this shows the bottom side of a board where capacitors could be mounted and out and away from the rest of the circuitry so that you can get them very close to the pins of the module. Again, we're showing some more applications of thermal vias conducting the heat down into the bottom layer, where the bottom layer could be exposed and easily eliminate the heat using the airflow that's in the system. Okay, some startup considerations. So this is where a hot swap controller can come into play. The hot swap controller can supervise a lot of these functions. So in terms of the module, you want to bring the input voltage up into the module, and when the module, when the input voltage is stable, you can activate the modules by turning the on-off control pin on. When the on-off control pin is on, the output will immediately start to rise, and when the output of the power module is stable, you can activate the loads and then go through the load power on sequence. This will result in the most stable operation for your system. Now, the hot swap controller that I talked about will control the inrush current. So if you're plugging into maybe a backplane, so the hot swap controller will limit the current, so when you plug that board in, you won't have arcing onto the backplane. It'll also control the inrush current and control a very controlled ramp up voltage to the module. And when that voltage is reached, it can turn on the power module, and then it can also activate the loads. Linear Technologies makes a nice one. I think it's a 4350. TI and Analog Devices also have hot swap controllers. Check them out. Now, what you don't want to do is you don't want to activate the load during the ramp up of the power module. Bad things can happen. Speaking of just one particular instance, the module could go into a current limit mode and oscillate back and forth, could disturb your loads. In other words, bad things can happen. You want to have a controlled startup at all times. Thermal management. In this application, airflow is the main consideration. We talked about 55 degrees C, 200 linear feet per minute. In most power systems design, the customer will design a custom heat sink. And in this photo, we're showing 3 modules with a common heat sink. It's very important all the modules will be kept at the same temperature. There is, between the heat sink and the base plate, there is a thermally conductive material that can take up any irregularities in the surface of the base plate and the surface of the heat sink. It's important to use the best material possible for that thermal interface so that you don't create a thermal resistance between the base plate and the heat sink. As with any systems design, the customer or you will have to verify the maximum temperatures, making sure that the module and all electronics are running well within their specifications. We detail some of this information in the data sheet, but the best way to confirm the module is to actually measure the base plate temperature during load conditions in your system with your airflow and fans and everything. And if you keep the base plate of these modules at or below 100 degrees C, you'll be well below the manufacturer's ratings of any of the components that we use in the module. And again, this is detailed in the data sheet. When you complete your design, you're going to want to verify that everything is working as designed. And so you're going to want to measure the current coming out of each module. Well, it's not recommended to add a resistor to the output of the module to measure this current. As stated before, the module has a very controlled 7 milliohm output impedance. Even if you add 1-2 milliohms to the output so that you can measure that current, it's going to disturb the current sharing. Most likely will improve the current sharing. So what you want to do is you want to measure the input current. Once you have the input current of the module, you know what the input voltage is, you can calculate the power coming from each module. With that information, you can plot the load sharing accuracy of the modules under different loading conditions. So here's an example of these DSQ 600 watt modules under test conditions. As you can see, we test this from 25 amp load to 100 amp load. So down here, they're delivering about 12.5 amps apiece. Up here, they're delivering full power at 50 amps apiece. We've zoomed in here on the input. We see that we have about a plus or minus half a amp down at the lower end. And at the higher end, we see 49, 51, plus or minus 1 amp. So in this condition, this layout, we have very good load sharing between 2 modules. You can expect the same in your design following some of these basic guidelines. So just to introduce you to a couple of modules, we have a 1/8 brick series that can deliver 12 volts at 400 watts. And the 1/4 brick, which we discussed here today, will deliver 12 volts at 600 watts with a 36 to 75 volt input range. Efficiency right around 96% for both of these modules. These modules provide input to output isolation with a basic insulation system. This requires a little bit of discussion. Most systems in a networking and telecom application will require an isolated intermediate bus. This provides a measure of safety for a technician that may be working on the system. Let's say, for example, there's an input failure of that N+1 system. It was struck by lightning, and all of a sudden there's 150 volts at the input to the converter. Well, that 150 volts won't show up at the output of the converter, destroying your circuit or providing a safety issue for any technician or service personnel that might be working on the system. These modules, as we've discussed, are designed for load sharing, and they're available in 2 different configurations, and there's no master-slave requirements. So package options for load sharing. We have a DSE, which is the 1/8 brick, or the DSQ, which is the 1/4 brick. They're DOSA compliant. For those of you who don't know, DOSA is an acronym for Distributed Power Open Standards Alliance. Several manufacturers of board mount power follow the DOSA standard for mechanical. So other suppliers may have a module that will basically fit into the same layout as these modules. Now the DSE or DSQ is also available with a PM bus, which we didn't discuss in this presentation. This might be my next presentation. There's a lot that goes into the PM bus. So this is an I2C communications line, okay, that's commonly used in all kinds of electronics, especially in the communications field. You can get some telemetry information from the power supplies, such as temperatures, load currents, and there's even a power goods signal on the output of the PM bus. So in the event that an isolated location, you have a power module failure, that information can be reported back to headquarters, and you can get somebody out there to fix the failed power module. But there's much more that the PM bus can do, including loop stability and many other features that you can access that are fully described in the data sheet. And again, this would be a whole nother presentation to review the PM bus process. The DCX is a 5-pin converter. So it basically has 3 pins on the input side, plus and minus VN in the on-off control. And on the output side, there's 2 pins for plus out and minus out. No PM bus. This is basically what we were talking about here today. Jason, I think that's all I have here. We can move on to the question and answers.
All right, thanks, Bill. Appreciate you walking us through that. I think I love hearing about where we're at now and even planning out your next presentation as well. That I think that's fantastic. So we've got a few questions that have come in here, and just as a reminder to everybody while we're going through these first few questions, if you have anything that's come to mind during Bill's presentation, definitely use that Q&A widget to submit questions to us, and let's just get rolling here. So Bill, first question is, can more than 2 modules be connected in parallel? And is there, a maximum number of modules that can be connected in parallel?
Well, theoretically, with the group load sharing, there is no maximum number. So any number of modules can be connected in parallel, theoretically. We have tested 3, maybe 4 modules in parallel, and most of our customers don't go above 3 or 4 modules connected in parallel.
All right, understood. We've got another question here. Is the trim and sense function available for the load sharing option?
No. Basically, that's eliminated because the output of the modules are trimmed at the factory at half load to plus or minus 1%. So you wouldn't want to have the user be able to adjust the output voltage or connect the sense lines in an improper fashion. So no, the trim and sense is not available in the load sharing versions.
Okay. Another question, do you have a particular recommendation for a load sharing controller?
I think we talked about that. The LTC, I can't remember the number. The LTC 4357 is what we're familiar with here at Murata. Again, we've used these in several of our front-end designs, and I've used these in several custom modules that we've designed for customers.
All right, got it. We just got another question in here. Do you have any particular recommendations or tips for just layout?
Well, we went through quite a few layout considerations here. Yeah, layout is critical. And I suggest that, review what we've gone over here. And again, we have applications engineering. We can put a customer in contact directly with one of our design engineers for layout assistance. We've actually taken several times schematics and files for PC board design, and we've done a review with the customer, recommended changes, whatever we believe. So we can assist with the design of a power system.
Got it. I know that's incredibly valuable for a lot of people. So I would really recommend for anyone out there to take advantage of those resources and get that individualized support when you're needing it. Another question that just came in, Bill, is the DSQ qualified as medical grade power supply?
No. I guess they would be looking at like a UL 60601 certification. No, but we do have a high isolation voltage and relatively low leakage currents. Honestly, we don't see a big demand for medical grade DC-DC converters. We have done some custom designs for medical grade, but as far as standard products go, I haven't released a medical grade power supply. I'd be very interested in talking with this particular person about the application, and maybe we can help out.
Perfect. And let's see, that was Ben who asked that question. Ben will be able to get you connected with Bill here to talk about some specifics for that afterwards as well. Are there any reference designs with circuits, layout, anything like that out there for people?
Other than the data sheet, I don't think I have a reference design. Again, I have a reference design here for this board that I referred to here a few times. This is basically the engineering design for testing and qualifying the part. I don't think I have a full reference design, including input filters, output filters, hot swap controllers, all that. But again, we have reviewed that with several customers.
Got it. Now, I know you talked about DOSA guidelines, and forgive me if you covered this question already, but we got the question, does the footprint follow DOSA guideline?
Yes, it does. These modules that we discussed here today and the 99% of the modules that we develop here are industry standard. A couple of industry standards, DOSA being one of the more popular for the brick modules, and then there's a couple of other pseudo-industry standards that we follow as well.
Cool, got it. Yeah, and there is another similar question here of, are your basically are your footprints industry standard? And I think we got that question there. So
yeah, the
great. Well, thank you, Bill.
Footprints are industry standard, but a warning that the modules themselves, the electronic design is different. So you would need to qualify, 2 suppliers in your application. It's not that you can just depend on designing around one supplier and dropping in another supplier. It's not that easy.
Understood. Well, Bill, I want to make sure to give people another couple minutes if there are any other questions that are coming in. Is there anything else, maybe as we might be getting close to wrapping up here, depending on other questions that might trickle in here, but is there anything else you want to make sure to emphasize or close off with here as we look like we're getting towards the end of the session?
Well, I hope everybody has my email address, and again, we're here to support you. We have applications engineers available. We have our design teams available to assist in any way we can with the module selection, whether it be layout, whether it be EMI filter design, or selecting a hot swap controller or an O-ring controller. We can help.
Fantastic. And what we can do, Bill, and for everyone here in attendance, there is this presentation, obviously, that's going to be on demand on All About Circuits. Everyone that's here attending live or is registered or is watching this later will also make sure that you have access to the slide deck here in PDF form, and Bill, that they've got your contact information as well so that they can reach out to you. Because I do think that the individualized, the kind of close attention that Murata gives in that support is really something special. So I really want to make sure everyone in our audience here gets the chance to take advantage of that. And anyone who is here, please feel free to reach out to them. They will definitely be able to get you where you need to go. So with that, I think that it looks like we've gotten through the log of questions here. So Bill, I want to thank you for coming and joining us here today.
Thank you, Jason. And thank
Absolutely.
you to thank you. Thank you.
What I will remind everyone who's here in attendance is that this is not the only webinar that Murata has done with us. It's not the only webinar that's on All About Circuits. If you look for other live and on-demand webinars on allaboutscircuits.com, you'll find lots of really good resources from Murata and other stuff going on in the industry right now. We look forward to seeing you all at the next live session that we'll have sometime soon, and hope that everyone out there stays safe and has a great continuation of their year. So thank you all for attending, and have a good day.